Okay, so let's talk a little bit about functions of three variables. So here, the input x, y, z, and the output is f of x, y, z. So first thing we want to say is that we cannot do what we did before in terms of having x and y as your input and then z as the output. We can't do that because we now have three inputs. So here's the best way to think of it. At each point, x, y, z, you have an output. So it might be that you're giving temperature based on location, right? So, or velocity based on location. So your input is now three variables. It's going to be very difficult to graph that function because that would require 4 dimensions. 3 for your input, 1 for your output, right? And it's very difficult for most of us to envision 4 dimensions. We can just kind of think of it in terms of snapshots of what happens, 3 dimensional snapshots in time, or like, like a running movie or something. It's got to be, it's hard to just have one picture capture that. Okay. So example, yeah, the temperature T at a point on the surface of the Earth depends on the longitude, the latitude of the point, and on the time T, right? Or you could have the longitude, latitude, and the distance from, I don't know, the center of the Earth or something. The altitude would be it, right? That'd be another way. Okay. Here's an example of a function. Find the domain if this is the formula.
It's 18 hours.
Thank you. If this is the algebraic formula of your function. So first thing we see is that we're going to need z to be bigger than y because you can't take the natural log of 0 and you can't take the natural log of a negative number. So we need z minus y to be bigger than 0. Z needs to be bigger than y. And that's about it because you can take sine of anything, right? So the domain is the set of points x, y, z in R3 such that z is strictly greater than y. What does this domain look like? If we were to sketch it, well, to say that you need z bigger than y, first thing we need to do, here's x, here's y, here's z. Now we need to sketch what does it mean to say that z is equal to y. Now, do you see how I have the zy plane right here? So I have the zy plane. And so now z equal to y is like that, right? But if I want z greater than y, then I need to take the top half of that. Now, to turn that into something that is three-dimensional, it's like I have a plane like that. Does that make sense? It's like here's z, here's y, here's x. And I'm saying take all of the points that are this top half, right? And that line right there, that plane is z equals y. Okay, so it's called half space because it's half of all the points. Yeah, I already mentioned this. It's very difficult to visualize a function of three variables by its graph because it would lie in four dimensions. But here's what we do. Instead of calling them level curves, we look at level surfaces. Here's an example. So what we're saying is we need to sketch the values based on the level surfaces of your graph. So what we're saying is imagine a function and the output is 9 for all of the points on this outer sphere. The output is 4 for all of the points on this yellow sphere, right? The output is 1 for all of the points on this pink sphere. So you get an idea. This is for the function of, and lots of times you might write w equals x squared plus y squared plus z squared, right? So the value of w is never negative, but it's getting bigger and bigger based on the sphere that you're in. And the level surfaces are concentric spheres. Concentric, that means they have the same center, and the center of those spheres is going to be the origin, and the radius is the square root of k. Okay? And so that is the main, so we're just sketching through here. There are just other examples. That's the main thing that I wanted to point out to you, is that you've got level surfaces when you have functions of 3 or more variables. Functions of 3 variables, okay? And that's it for our introduction to functions of several variables. For what we're going to do, what are we going to do next with this? We're going to start looking at rates of change. So we're going to look at tangent planes and partial derivatives and gradients.